Hi everyone. Today I'm going to be showing you how to use some software called GeoGebra in order to create a mathematical model of a real world application. Now the first thing I'm going to do is I'm going to use the tool menu here, and I'll go to where it says image. I will upload this image that I found, this one and saved it earlier, and so this is the one that I want to work on. And a couple of things to note: the image itself has two corner points here, A and B. I can drag the points around to enlarge the image or to rotate the image. So I think I'll just set the image like that. Now, it's important when I'm working here that I'm using the moving tool, not one of these other tools. So the curve that I want to work on, and there's a lot of curves here in this image. Oh, and the other thing is, if you grab the image, you'll move the image. If you grab the grid outside, you'll move the entire window. So that's a little bit tricky to get used to. Now, the point or the part of the image that I want to work on for my mathematical model is the curve that starts here at the corner of the diver's chest, runs along the front of their body, down the leg, around past the ankle, and then finishing at this spot here at the corner of the fin. That looks like a nice smooth curve that I could use a polynomial function to model. So how to work? Well, let's just go to my notes for a moment. I know that a third degree polynomial would have a typical sort of a bendy S shape to it, like I've sketched there. I also know there's different ways to write the formula for a third degree polynomial, one of which is this, where we have alpha, beta and gamma, the roots of the equation, the values where the function crosses the x-axis of the roots of the equation. Now that would give me three key values into my formula. The only one missing there would be the value of a, and I calculate, or I could find the value of a if I had another data point, a fourth data point, to work with. So there's my goal. I need to get my function, or my curve, looking like this. So let's move the entire thing down a bit until the curve is crossing the x-axis. Now it gets a little bit difficult to see, so I'll do a right click on the image, go to the settings, and under the color tab, reduce the opacity of the image a bit, and that makes it much easier to see the grid lines. Now I'm going to select the point tool here, and I'm going to try and, as carefully as I can, place a point at the appropriate spots there for the roots of the equation, and then one more point somewhere over the edge of the curve. If I use the algebra tab, you can see, remember, point A and point B were the points at the bottom of the image. I don't really care about them. And here's point C, D, E and F. It seems like point C, this one, is not quite on the x-axis. So I'm just using my mouse wheel there to zoom on in. Yeah, it looks like I missed a bit, didn't it? So I'll adjust that more carefully there. And now I'm getting oodles of decimal places, which I didn't really need that many decimal places for. That's better. So it's locked onto that point nicely. Now the other thing to consider, of course, is when I zoom in, the boundary between this red and white region isn't so clearly defined as when I've zoomed out. So there is some things to think about there, isn't there? So there's my points, and I'm going to have to go back to my working page and use those numbers. In order to stop me from forgetting, I'll just do a little screen snip of those numbers and take them back to my working page. So let's just paste them in, hopefully somewhere that's not going to get in the way. Okay, now let's see if we can do some working here. So my formula is y equals a x take. Now, where was the first one? Well, that one there could be the value of alpha, that one could be the value of beta, and that one could be the value of gamma. So we would have 2.46, x take away 5, that was convenient, and x take away 7. I've almost got my formula. If I substitute the value of 5.9 for x and 0.58 for y, I could calculate the unknown value of a. So 0.58 would equal the unknown value a, 5.9 take 2.46, 5.9 take 5, and 5.9 take 7. Obviously, I'll need a calculator to help me, so I'll just see. There we go. Now, I might pause for a moment while I figure this out. Okay, here we are. So I've done that calculation, and it seems like the value of A was negative 0.170. I'm pretty sure that's what it said, if I just double check. Negative 0.170. Yeah, there's a few more digits. So my next job is to write the equation then. So my formula for the curve that I think will work is 0.170, x take 2.46, x take 5, x take 7. That function, I hope, is going to hit those 4 points that I selected and, fingers crossed, be a good model for the curve that I'm working with. So I'll just take a moment to go and type that into GeoGebra. Okay, there we are. So I've typed the formula into GeoGebra here as we calculated, and there's my mathematical model. Let's judge to see how well I've done. Well, it definitely hits the 4 data points that I had selected, so that part of the model is good, means it's mathematically correct. But is it a high fidelity model? Is the model matching the real world curve that I was looking at? Not really, because the real curve runs along here, but my mathematical formula dips way too deep. And this part here is reasonably close, but it misses there, doesn't it? And it starts to miss on the other side here. So as far as my model goes, it's doing a bad job of matching the real picture that I was working on. As far as being correct, mathematically it is correct working, it's just a poor choice. I made the assumption that a third-degree polynomial would match that curve. It seems that my assumption wasn't correct. Now that's a first attempt though, and I'm going to stop now and I'll come back with another one where we do a better job. Thanks for watching.